Okay, cool. So yeah, welcome back. This is, I guess, the last session of the workshop, and it's my honor to do this with you. Because besides the most exciting part, integrating the data yesterday in Cytoscape, we're even gonna now set an additional layer on top of that, so it becomes even more exciting. And we want to integrate some of the statistic results now. Then while doing that, I also want to like take a look at like some of the plots with you and like just do some interpretation of like the results, what's going on. And then I would encourage you to take some time to also explore it by yourself. And then maybe at the very end, we can have a brief discussion, and some of you can maybe tell the others what you found and what you think is like the most important molecular features in driving like this different like locations. Okay, but before we get there, I just want to contextualize a little bit like the data set that we've been working with. And this is data we looked at in many different occasions. So initially, this is from a study that we published about just like a spatial survey and coastal San Diego area. Partially, this was inspired by figuring out what are like the safest spots to surf after rainfall, because people typically tell you if it's raining and like dirty water is coming into like the coastal systems, then stay out of the water. And we just wanted to know, are there like spatial gradients? And then later on, as this data set was quite nice in terms of like differences in samples, both from a spatial but also from a temporal perspective. We used this for a couple of occasions, including as a test data set for the Hitchhiker's Guide that Upstairs spearheaded and many people contributed to. So if you want to take a look at that preprint paper, hopefully also at some point published, then you will see the same data set. This here is a subset of it, so it's only one time point. We have in a total 3, but for like simplicity reasons, we only focused on one batch now, so we don't have to argue and deal about batch effects and all of that. But yeah, just to tell you what we did, we basically deployed like a little boat and cruised down the San Diego coast here, from like the north here, Torrey Pines State Park, all the way down along like the La Jolla Reefs to like Mission Bay, which is a larger bay with like a big marina area in San Diego that also have a river mouth, right? And just so you know, there's 2 potential point sources that we already knew of. This is the San Diego River here and Mission Bay. You can see the mouth coming out here at the very bottom. And then also there's a lagoon, Los Pensanquitos Lagoon, in the very north at the Torrey Pines State Park, where there's also different creeks and like some fresh water, coming into this lagoon, and it's also draining out, especially after significant rainfall. So now at the time when we sampled this in winter 2017, 2018, there was like one or like several major rain events. And these data that we looked at today was collected a couple of days after some significant rainfall, right? So we assumed that there was major discharge through these river systems, and hence we would assume, or the hypothesis would be, that those locations should probably show higher loads of like xenobiotics and maybe other like terrestrial molecules. Also, to go to our non-target metabolomics pipeline, so what we did was we sampled 1 liter of seawater at each of those spots in biological duplicates. So there should be 2 individual samples at each station. And then we solid phase extracted this with PPL resin. This is a common resin used for like solid phase extraction. And then we run non-targeted LC-MS-MS pretty much in the fashion that Allegra presented to you, so in data-dependent acquisition. And then we converted this to MZML files, and that is basically where all of you started processing this data, right? We used MZMine3 with Stefan to pick the features, and then we used now GMPS2 to create molecular networks and do like the spectrum library matching. And then with Marcus yesterday, you did the Sirius in silico annotation, right? Before we then merged this data in Cytoscape, and this morning pushed it through our FBMN stats pipeline. So in our case here, the web app, but for this purpose, we also run those in our Jupyter notebooks, which give you a little bit more flexibility and more options to do that. And yeah, I just want to reiterate really quickly on what way to choose if you want to follow this hitchhiker guide. So this is all part of a larger protocols paper that we wrote, which I think should be a good starting point if you want to do statistical analysis. As yours has showed you, there's also other tools that are excellent, like MetaboAnalyst would be one of those. And I'm sure there's many other Python and R pipelines that people developed. So there's a lot of like different ways to do exactly the same thing. What we do, but obviously as we wrote this is what we control. So for like the workshop, and like also if I had to recommend you something, I would probably pick this. And the reason is that this kind of like scales a little bit like to the needs you might have. And to guide you through that, we have like this decision tree that is part of like the protocols paper, and it just like tells you, okay, where do I start with, right? And I think main two factors are what is your experience and willingness to do scripting, and then what is the scale of like the samples, right? So how many samples do you have and how complex are those? And yeah, to make things easy, if you don't want to deal with scripting and say, oh, Python or R or notebooks, I don't want to deal with it. That's why we have like this web app. And also the reason we used it here is because I think this is like the easiest way to do the analysis. So that's why we highlighted now like the web app here. But then if you want to do this like more professionally, I would suggest to go and use like either the Colab notebooks or the Jupyter notebooks. And then it pretty much depends on what sample size you have. So for smaller sample sets, I think Colab is excellent. You can like just like run it in your web browser. You don't have to install or download anything. And if you have like larger sample sets, so then maybe it does not cut it anymore, or it's going to get really slow. So then I think it makes sense to download the Jupyter notebook and do the entire thing locally on your computer. And then you just have to choose whether you want to use Python or R. And I think this is pretty much depending on you, whether one or the other thing is your preference. I think the R notebooks are a little bit more developed because that is what Upser's strength is. And I think she dedicated a lot of time on writing those. So if you write us, that would be also probably the thing we can help you most with. But yeah, if you work with Python all the time, then I obviously would suggest to use Python. If you're dealing with microbiome data, then you may have experiences with QIIME 2. So then it might be also useful to actually use the QIIME 2 metabolomics plugins that we have, and then yeah, use the notebook with QIIME 2. Although this is, I think, right now like the most limited notebook. Okay, but for now, we already agreed on that we would use the web app, and I hope all of you got it running either one way or the other, right? So we kind of like gave you two options, either to download like the .exe files and then run it in like a local fashion through the, can you just leave it? I think it's fine. So to run it like in a local fashion, right? And the other option would be just to use the regular web app. Normally, we would recommend to use the web app, but due to efficiency reasons and server capacity, like dealing with like 60 people, I think here in this context, the local web app would be like the tool of choice. It does not support the PCOA, as there's a package not running under Windows, so that's a limitation, of course, but I think for today, that doesn't matter. If you go home and you want to use it, then use the web app, and this should be fine. And then hopefully at that moment, not 60 people should use it at the same time. All right. Okay, so yeah, just to highlight it again, this all is basically coming together with like this like tutorial / protocols paper that we have. So basically each of the steps is explained in detail in this paper. It got pretty long, so I don't think you need to like read it from the beginning to the end. But as you go through like this either notebook or web app, I think it's good to have this on the side, you know, and then if you have questions, maybe you can like read a little bit through that. All right. So who of you got to this point and processed their data either in the web app, online or local? Can I see some hands? Okay, it's good. I'm glad. Most of you got it. Who still was struggling and could not get it running? Okay, one person, only one person. Great. Then if you want, we can chat afterwards, and we can give you a hand. But yeah, what we basically did, or what Apsa did, was she loaded the task ID from the very same GMPOS job as Giovanni into like this file selection section, and then loaded the files into the web app to then do like the Planck subtraction and imputation and normalization. And I think at this point, I just want to go to my web browser and do the rest with you interactively. So, and I loaded it already before, so I don't have to wait too long now to do the individual steps. So yeah, you process the data, right? And then we did like this initial PCA visualization. And then you should have seen something like that. So now just for fun, as you downloaded the feature table before and the metadata, you could have also uploaded it to a Metabo Analyst or run it in whatever scripts you have. And like here, like your PCA or PCOA with an Euclidean distance metric should hopefully show you like a very similar picture, right? So now typically in our pipeline, this is like the first thing we do to like look at the data because it's like unsupervised and it just gives you an idea on how different things are. And then if we can like play around with like the different metadata categories here, we could check, do we have a batch effect? Do I see clustering based on batch? Okay, we only have one batch here, so that seems not to be an issue. And then this is also all from the same months and year, right? So we could check for those. And then perhaps now most interestingly, we could use like the sample area and then check, do we see significant or like clustering between like the different locations? So now, and this is a little bit of pity that the Permanova and PCOA does not work here. Now I would also run the Permanova to estimate like significance of these clusterings, right? So then on the web app online version, you could do that. You would just like then select sample area to run the Permanova, and it would tell you, well, this is like either significant or not. But just by eyeballing it, I see already some friends here, right? So we see like this clusters based on like the different sample location indicated through the colors. So that is already fairly interesting. And then now with like that initial context I gave you, right, that we have two putative point sources where we know that there should be larger discharge of like fresh water after the rain event, right? We can already like kind of like test a first like hypothesis whether like that could explain, like chemical differences within our metabolomics data. And then, yeah, as I mentioned, Mission Bay, this is like one of the, like the areas where we would assume that the San Diego River should like kind of like go in. So, and that we see here kind of like it's a little bit separated. And then also like the Torrey Pines area, right? That's the very north of this area, seems to be a little bit away. And then like the La Jolla Reefs, La Jolla Cove, and also here Pacific Beach. So those were like the spots in the middle. They have like quite some variance, but they're like a little bit like away from like this other two spots, right? So that is already interesting, and I would be fairly happy with like this initial result. Oh, I think because it's probably very much dominated by compounds that come in from like the river discharge. So we also saw that in the salinity dropping right in this area. So this is an oceanographic way of like estimating freshwater like contribution to this area, and it was clearly distinct, right? You could probably also just see it by the turbidity of like the water and see, okay, there's probably more discharge. So to be fair, we were really like comparing very different things. So it's not too surprising that we would pick that up with PCA. But just as a first sanity check, I think this is a good way to do it. But then, yeah, Apsa showed you some supervised methods in form of like the random forest, right? To like use basically like this three generation and explanation of distinction of like the different sample areas by removing individual features out of the equation and then kind of assigning mean decreased accuracies, so importance to each of those features in explaining like this difference, right? So that would basically provide you like a long list with all the features ranked by that importance or mean decreased accuracy score that you have now as a table. And then she also did some univariate tests with like the ANOVA and Tukey to generate like here this ANOVA plot, and I hope it's still loaded. Yes. And then you inspected already some individual features with like the box plots, which I think is a great way to follow up on that, right? To really like look at like the individual data points as well and see, is there actually a difference? All right, and now you have like these tables. They're hopefully on your computer. If not, then you can find them also here in the Eco-Metabolomics workshop folder under FBMN stats. So if you go there, if you don't want to download it from the app now by yourself, you could just like download like the tables here. And again, I just want to stress, that you can like open those in a text editor or in Excel, and then we can also like modify those. And that in a second we want to do, because there's a couple of steps we may need to do and transform these data frames before we can bring them in to Cytoscape. Okay, I asked you who has the networks in Cytoscape before. Do all of you have the networks open now in Cytoscape? Okay, if not, that's the time now to open it. I hopefully still have it open. Yes, that's where we basically left yesterday. And I even have like the same styles, with the pie charts, and I have like the imported annotations, from Sirius and from like the networks and so on. And that's also a good point, like why I don't think it's important to merge in the annotations at the stats level, because now if I bring in those values into like my table here in Cytoscape, then obviously I will have the annotations again, and I will even have more because I have the serious molecular formulas, class levels, and so on. So yeah, how do we get now the values in there, and what do we actually want to import, right? So one very basic thing, and we didn't touch up on that much before, is so this network, when I zoom out, this is of course kind of like my whole data set, right? So although we did some filtering in MZMine, right, we didn't do any Planck subtraction at all. So this is really like the full data set we initially had. But now, thanks to like the Planck removal during like the statistical analysis, right, we kind of like know now, okay, which features are likely to come from like our process Plancks and which ones seem to be more likely to actually come from like the samples. So as a very first step, what I want to do is I just want to basically subset this larger network and just like assign now the binary identifier whether something is a feature from like the Planck or from like the samples. Right? And what I simply do there is that I go to like the downloaded files that I just downloaded from like the Google Drive, right? From the FBMN stats folder. And there is like this Planck remove table or Planck remove the scaled table. They should all have the same number of rows than just like the values for the peak area vary. And then, yeah, just gonna open one of those in Excel. Okay, and now what we should see here is that actually this is the data frame, right? And if you look very carefully, you will see already that actually it's transposed, right? So that the features are now like in the different uh, columns, and then the sample names here are in the different rows. So I quickly, or actually, let me just leave that open, but I quickly gonna check one of the others if that is already back transposed. If not, I have to manually, or I have to do it in one step in Excel. Okay, it's the same thing. So, all right. Then I just gonna take that full table here. Oops. And copy it into a new sheet. And then on the paste options, I select this transpose thing. And then you will see that now I have my features back in the different rows, right? And then now also interestingly, you see there's also this attributes, right? So these are the different metadata categories. So that is already integrated. So now obviously for the thing I want to do, I don't need them. So then I can just delete them. And now I basically have my feature table as I had it before, but just after Planck subtraction. And one thing you will notice is that now instead of the 5,800 or whatever my node number was here, yeah, 5,882, I only have 4,854 rows, right? So there's 1,000 features we removed during the Planck removal steps. And now what I can do here is I can just say, okay, all those features should be actually from the samples. So I could generate a new column here and then call this Planck removed or something. And then just say, this is a true feature, and then assign this value to all of them. And now, as we learned yesterday, it's not very difficult to import this back into Cytoscale. All I need is the feature ID, right? So now there's only one thing that might be a little bit complicated, but it's not too bad, that this feature ID is buried in that string here, right? Because what the app does is it combines the feature number with the mass and the retention time. But I have like this underscore as a delimiter. So I just generate here a couple of like new columns and then use like the data text to columns option in Excel. And then based on like the underscore as a delimiter, I can actually split those. All right. Okay, here's the option, right? So I say next, and then I just say here, other character, underscore, use this please, and then split me this into like different columns, and then I just say, okay, this here is the scan ID or feature number or whatever. And then I remove the rest because for now I don't need them. And then I could put those two into a new column and then save this as my binary identifier for Planck removal. Right, so quickly do that. Save as binary Planck removed. Okay. Get a warning that this is only saving this one sheet, but that's fine. And then now in the very same fashion as I imported yesterday the annotations from Sirius, I can go to File, Import, Table from File, right? And then under my FBMN stats folder, there should be the bin Planck removed thing. And then, now it even like pre-selected it already correctly for me. And I have here like the key for the scan number and then Planck removed. And then I just say, okay. And now I have this hopefully in my table. And then you will see that here in this table, some of those have a Planck value. Those are obviously the ones that were not in my feature table after Planck removal. So those are like the ones I want to remove. And what I like much better is removing them is actually just copying the ones I want into a new network, right? Therefore, I would simply sort by like the Planck removed header and then go all the way down till where there is no more Planck removed features, select them all, and then right click and say select nodes from selected rows. And then you will see here in the network that it now selects my features that are still there after the Planck removal. And we can also see already that one of those big ones are not yellow. That is good because remember those were the ones that are the contaminant from septum vial thing. So hopefully we get rid of them now. And then, yeah, I just go to File, New Network, from selected nodes, all edges. And then what it should generate is a new network that is now basically subset to only like the networks I want. And you will see now that there is, unfortunately, a couple of holes in there, right? So technically, it doesn't really matter, but it somehow does not look good because there's now a lot of singletons that are eventually up there. If I want to reorganize this, then I can just like go on layout and then apply preferred layout. And then, yeah, nicely, Cytoscape is like rearranging them as well in like an order, and all the higher connected nodes are on the top and like the lower ones are at the bottom. All right, so now you kind of like have a cleaned up network, and when you like browse in there, then you should hopefully find less artifacts that are actually coming from your planks. But okay, so now we want to figure out what matters within that data, right? And now a very straightforward way to do that is to load in like the mean decreased accuracies from like our random forest classification as an additional attribute. So therefore, I would do the very same thing as I just did. I would go to my FBMN stats folder, and there should be the importance scores from the random forest with 500 decision trees. Hopefully it will let me open that in Excel. And then I probably need to do the same type of like splitting of like the columns, what I just did. And maybe I should also close the other files first. Okay, yes. All right, great. So now, actually, let me close the other things first. So I don't need them anymore. So yeah, basically just the same as before. I will split those columns here based on like the underscore as a delimiter. So same as before, underscore, finish, and then we have a new scan, and then the importance score here. So now I'm just gonna save this as a TSV or CSV file. Okay, just overwrite. All right, and then in the very same fashion as before, I will now import this under File, Import, Table from File, and then use the importance score of my trees. Let's see if it takes it. Nice. Scan as a key, and then the importance as values. And now, again, as a new column, I should have those, right? And now I can just play around with like basically like the scores here. I can either sort them here directly and then let me bring like to the most important ones, or I could also use this for some mapping and, for example, set the node size based on like this importance score. So if we want to do that, I would go back to style and then use here like the size mapper that I set at my manually made some precursor intensity yesterday, and then just instead select the importance score here. And then I may need to adjust this continuous mapper. So I will set or reset the min and max, and then maybe make it even more extreme. And now looking at the network, hopefully I will directly be guided to some of like the nodes with like the highest mean decreased accuracy. So I could then either zoom in there and kind of like investigate what those things are, right? Or I could also then copy them and put them into like a new network, you know, as I move on with my like data analysis. So now I'm of course interested in finding some things that I have high confidence in their annotation, right? And as you can see here right now, it still has like some class level annotation from Canopus. So that's maybe not like the most confident annotation that we have. So I probably would change the label to my GMPS library ID, compound name, you know, and then I see, oh, okay, those are like not annotated. So maybe in order to do this a little bit faster, I would just go to like the column here with like the library ID compound name, you know, and then as I sorted it already by mean decreased accuracy, look at like the first hit. So there's phaeophytin. So I think this is like a chlorophyll breakdown product. So it's probably there in the ocean. And then, you know, we can like move on. So there's here a mass bank entry, simazine, you know, that sounds already like a little bit like a pesticide to me. So we could now follow up on that, right? I also see here the component is -1. So this means that this is not connected in a network because it's, yeah, a singleton. Maybe not like the best example, but then, yeah, I can just like scroll down the line and look at other things. So here we have a phosphocholine and then more phaeophytin, more phosphocholine, and then some other features. Obviously, I could also now just further filter that, right? If I would open this in Excel, I could like put different categories and then only look at like the mean decreased accuracies for my highest confident annotated compounds. And that's typically one way how we would deal with it. Fortunately, we still have like here contaminant from the septum. So that could be now a question, did like the Planck subtraction fail here? Or maybe this is also like a pollutant that's in the water. So something to watch out for. And then, yeah, we could move on and check like the different features. So now I'm wondering, did I actually sort by mean decreased accuracy? Yes. Because from memory, I know a couple of compounds that seem to have very strong patterns and also have some very interesting explanations. All right. But maybe that's now a point where I would also leave it a little bit up to you to like scroll through like the data and maybe tell me and the others what you think could actually matter in this data set. And then we can like discuss this and then further yeah, visualize it. So do you want to take like 1 or 2 minutes and just quickly browse through and I see if I find the one that I like? All right. I guess, well, I'm gonna start with like the compound that was most interesting from my perspective here, because this is a purely data-driven now way to look at it, right? And I don't want to be biased about my chemistry knowledge or whatsoever. So I just gonna pick the first one that seemed to be a xenobiotic that was highly ranked according like to the random forest importance score, right? And this is here simazine. So the reason why I like it is because it's from the mass bank spectral library. And I know that in mass bank, there's a lot of like xenobiotics, and it also does not sound like a natural product. But in order to verify that, I really have to actually look it up, right? And like figure out what it is. But a very straightforward way to do that is just to copy its name and then go back to my browser and actually quickly Google it. And then, oh yes, there's a chlorine, there's like this um, triazine ring, right? I see already some pictures from some herbicides, and yeah, this is definitely seems to be like an anthropogenic compound, right? So that would be really interesting. And yeah, statistically, at least from like my random forest classification, that seemed to like play some importance in classifying like the different sample areas. So we should probably take a closer look at that. And to do that, what I would do is I would just like take now here either like the shared name, and like go and like visualize this as a box plot, or I can also quickly look at it in the network and see, are there actually other related compounds that have similar patterns, right? So now I can tell you already it might be not that exciting because this has the component index -1, which means that it does not have a network. But if it had one, how to do that is if you want to navigate your network and you want to find something in particular, then you can use here like this filter tab and then select the column filter and the category. In my case, here, node, library, compound name, and then hit here Zim, right? And then I get it. And then I can just hit here like the magnifying class with the check mark. And then hopefully this will bring me directly to like this node. And then, yeah, you will see it's, as I said, among like the singletons down here. So nothing networked with it, right? But I see already from like my pie chart, right, that, oh, there's only like 2 sample spots where that seem to be high abundant. Now, obviously, I want to follow up on it, right? So I know now the shared name, which is like the feature ID. So I can go back to the app. And this is, I think, where this really starts to work together, And then I select, what was the number? 6047. All right, so let's select this. And then, okay. Oh, okay. So, but then it's location 10 and 11, right? Where it's very high sample area. So may need to rerun that. Anyway, so while this reruns, so this would be one purely data-driven way to look at it, right? But I mentioned already to you that from my memory, I also had some other compounds in mind that I thought would be interesting, right? And now, obviously, we worked a lot with this data, so I looked at it a couple of times. But if that would be a brand new data set, then literally, like the first thing that I normally do is I browse through like this list of annotations at the beginning. Because as a chemist, I really want to know what molecules are in there, right? And while this is some sort biased towards like chemical knowledge, I think it's also a good way to look at this depth from that direction, right? And that's why I think we fundamentally want to do the annotation first before we do any statistical tests, so we don't lose anything on the way, right? Because there might be something that actually has like just a small difference, but by its chemical identity, it really matters, right? Especially if this is a toxin or like a cancerogenic compound or something that we know, oh, that might be important, right? So yeah, that way I would always scroll through this. And if I am not too mistaken, there is this compound Egarol that is a herbicide that is used in boat paint. And the interesting thing too is that this is not allowed. It's been a long time banned in the European Union, but I think it's still on the market in North America. So now with the marina and like the, boats and influences there at Mission Bay in mind, such a compound that could be an indicator of, like boat paint would be, of course, like interesting for us. So I now also know here the scan number, right? So that way I could like search for it either in my network and see if this is still there, after the Planck subtraction, or whether this was maybe a contaminant. So I would go here to my shared name and then search by this number. And then, oh yeah, nicely, this is actually still there. And now if I scroll to the right, then yeah, it has like a lower importance score in the random forest. So this was still maybe playing a role, but like, yeah, its importance was not as high as the other features that were higher up. But from a chemical context, to me, this is important. All right, and then also I see, oh, this now has a component, right? 227, so that might be interesting because there are some related compounds. So let's take a look at that. We can hit the check mark with the magnifying glass, and then we directly see, oh, there's Igarol connected in a network. There's another node next to it that has a similar pattern in like this pie chart. So that means that it's at the same spot, right? It's not annotated. So it's maybe something new, right? And then there's some other related nodes, but they all have like this like a more rainbow color pattern in like the pie chart. So they may be more ambiguous, right? But yeah, these two are interesting for me. So now, of course, I want to think about a little bit more and know what that might could be. So now, how would you address this? So it's not annotated here by the library. What would be the first thing you could do? Exactly. I can like, check like the other annotations and then, maybe I get already some answers there. Easiest way without changing now the style is I just like select the two and then they're like connected next to each other. And then we would see, okay, they have very different molecular formulas. That's interesting, right? One is like with 5 nitrogen and sulfur, and one is with like 2 oxygen and phosphorus. But they have very similar MS-MS spectra. Who of you believes the molecular formulas? Hmm? Yeah. It could have been that the second reported one would have been the right one. I have serious doubts about those molecular formulas, so I wouldn't believe those. Interestingly, both classifier classes here classify it as the same molecule, right? So that is weird. And then also here the smile string, which like tells me the structure, that is also very similar. And actually, I don't see any phosphorus in there. Mhm. So definitely precursor formula I would not trust in this case, right? This here could be cool. That could be maybe a thing. And then, yeah, I'm happy that I have the same classifier compounds. And then now if I switch quickly to the edge table, and I just want to take a look at this edge, I would check the cosine. It has 0.94 cosine score. So this is a very good agreement on MS-MS similarity. Now, of course, if this would be something I want to build a story up, then I would display actually the spectra. And later on, I will say a word or two about that. But so far, I trust this. I don't trust the molecular formula, but I trust the classifier thing because it tells me what I want to hear, that these things are similar. And now, most importantly, I want to take a look at the structure from Igarol and then try and think about whether like that difference could make any sense chemically, right? And you could have already guessed that what was okay. Let's quickly put the mass delta in the network through here, the style tab, and then we use like the label, and then we use delta MZ as a pass-through mapper. So yeah, 40. 40 is the mass difference. What could 40 be? And I have an idea, but let's quickly check the structure of Igarol because I don't fully remember. So yes, this is also like this triazine compound here, right? We have a sulfur, so that fits to like the CSI finger ID derived structure, right? And then, oh yeah, I heard it already. What is it? So there's a cyclopropene group, right? And now if you quickly calculate it, and yeah, it's like 3 carbons and 4 hydrogens, right? 5, right? I guess we're getting close to 40. So could that be like losing here like the cyclopropane group, right? And now, and this I now remember, now a bell is ringing. And you can actually quickly Google it. Google if there is a dicyclopropane Igarol derivative that is found. And if I'm not completely mistaken, then I think that is a biodegradation product of particularly this xenobiotic. All right, long story short, I think this is an interesting hit. It was not highly ranked in the random forest, but still it could be. I think before we close, I just want to dive for just a minute or two into the smile strings, because this is another thing that I find super useful. So who of you is regularly using Smiles code? 1, 2, 3. Okay, a couple of you. Okay, so to those of you who do not regularly use it, I would highly recommend it, because at the very, very minimum, what you can use this for is to quickly draw your structures, because you may want to now get this, right? And then generic program for me would be ChemDraw. I hope most of you have a license through your university. If not, there's open source options such as ChemSketch, and you can import the Smiles code, and then it just like draws the structure for you, right? And as they seem already very similar here just in the smile string, I have the feeling that this may tells me exactly what I want to know and what I hope should be the case. So I'm gonna quickly open my ChemDraw. I hope my license is still good. Oh, but there's the 10 free trials. So I just use that one for now. Okay. And then ChemDraw is popping up. And then I copied the smile string. And all I need to do is hopefully paste this in. And then, oh, do you remember the other structure? Okay. And that was there already as well. So, wow. So CSI Finger ID actually got it right? So first of all, it ID'd Igarol, like clearly the structure. And then what we already expected, that this could be a loss of this propane unit seems also to be the case according to the in silico match from CSI Finger ID. So now, of course, this is still somewhat level 2, level 3 IDs, right? So this is not something I would claim is like 100% true, but I think we have multiple layers of evidence. So I would be very positive about it. So, okay, that brings me to like the last thing. So what do you think should be now the next step if I say, okay, this is a cool example. Okay, we may have to redo like the scaling and TIC normalization to like check like box plots and significance in the app. But if I want to follow up on that, what would be like the next steps that you would do if this was your study? and you want to write this in your paper. Yes, I would definitely take a look at the mass spectra, right? We could now open them in MZMine, or I personally use the GMPS dashboard because it's directly online. So I could go online and just look for like this mass in the original files and visualize the mass spectra. And then I could compare them already, right, between the two. And then I could also look at the mirror match. This I actually can do directly here in GMPS2, right? There's like this mirror match button. So I inspect already like the MS-MS match, right? And was like, oh, that is beautiful. That is really good. So I would say, and most importantly here, like the small peaks, they all seem to be explained. Hence, oh, here without filtering, right? It has even a higher cosine score than in my networking job. So this is really good. Now I could also load in that other compound, right? Look at the mirror match between like the des-iso propane agarol. See, I would hopefully assume that some of those peaks are shifted by 40 Thomson. So that would be the next thing. Then what else? We have more confidence now in our spectral match, but it's still level 2 or level 3, right? So what would be the next step to further verify? Exactly. Exactly. So I would for sure order the standard, right? To like confirm it as a level 1 ID by MS-MS matching and retention time, ideally with 2 orthogonal chromatographic methods, right? Then it's really bulletproof. So you get further evidence, right? Then hopefully des-iso propane agarol is also available. If it's not, then maybe you have to make it, right? Or to like even verify it in a biological context, right? I said already, well, I think that this might be like a biodegradation product, right? I could do an incubation experiment, right? And maybe just like incubate it in like seawater to see if some of like the microbes present in there actually like make this compound, right? And I think these types of like downstream verifications are super, super important. So all we do here is we prioritize features and we point something that we think might be important. But I think at the end, this is hypothesis generating, right? And you need to do downstream hypothesis testing. Can be as simple as verifying it as a level 1 ID, but then often other follow-up studies are wanted. And I think depending on the scope of your study, that might be something you want to do, or the reviewer too will ask you to do, hopefully. Right. I think this was pretty much I wanted to show you. We'll still hang out for like a little bit and troubleshoot issues with whatever analysis steps you might get hung up at, or talk about other things. Thanks a lot for listening, and I hope this is useful.